study them. I'll tell you about conformal defects. So I'll tell you what conformal defects are, why we should care about them, and how we study them. Okay, so well, first of all, let me remind you the conformal field theories. The fields are important. Why are they important? Because they occur as the fixed points of renormalization group flow. They are special points in this space of quantum field theory, and they also describe physics near a second order phase transition. So that's why we should study conformal field theories. And now, just like human beings, conformal field theories sometimes can have defects. And rather than ignoring them, we should study them. Okay, so well, in particular, sometimes the defects modify the behavior of conformal field theory. So if you have I will explain what I mean by defect, but if you have a defect, they modify the observables that you can measure in an experiment. The plan of the talk is to introduce the defect through two examples. Both of them are old examples. One of them is a very famous example called the Kondo effect. And the second example is going to be the twist defect in Ising model. Okay, so let's get started. I will start with the Kondo effect. So a little bit of history. So in 50s, okay, so yeah, I will talk about the Kondo effect has to do with metals. So what are metals? Well, we think of metals as well. The physics of metals is usually described by just free electrons in the conduction band. And if you measure the resistivity of a metal, you expect that when you lower the temperature, the resistivity should go down. This is because resistivity occurs from collisions of electrons with phonon vibrations, and this should go down as the temperature is lower. But there are some experiments of metals in the presence of impurities where they found that if you measure the resistivity as a function of temperature, there was this funny dip. What they found is that resistivity goes down, but then it goes up. This was at very low temperatures. There are many experiments. In particular, if you look at gold in the presence of iron impurities, you will find this. This is around 5 Kelvin, and like such a small temperature, so like 5 Kelvin, 10 Kelvin. And then Kondo in 1964 gave a model that would explain this. The model is a very simple model. It's just the usual Hamiltonian that you write down for the for fermions in a metal plus an impurity term. So this, I claim, can be explained by this Hamiltonian. Plus impurity. So what's happening here is that, so let me explain this equation. I'm writing down the Hamiltonian of a bunch of free fermions moving in the conduction band. Epsilon k is the energy of the fermions above the Fermi level, and sorry, k is the momentum level. So, and these operators are just creation and annihilation operators. This operator will annihilate a fermion of momentum k, and this operator will create a fermion of momentum k. And what Condor did was he added a term where these fermions can interact with this spin impurity. What is S? S just labels the spin of an impurity atom, say. And these sigmas are just, the usual sigma matrices, so the usual Pauli matrices. Okay, so now how can one check that this impurity term will? So let me first explain how this is the defect. So if you go to the language of action, adding this term to the Hamiltonian literally just means including in the action a term that looks like just lambda s dot psi dagger at the origin. So
What is this S vector outside?
yeah,
Why cannot you take it just whatever x direction and replace sigma by sigma x?
yes,
if it is just a constant, I don't know about Condor model. Is it a constant out front of?
Yeah, it's a constant.
So you could have replaced sigma by sigma z.
You could do that. You could pick a direction in.
It's just a direction along which impurities are operating.
That's right. Yeah.
Oh, okay.
And also the momentum is not conserved in the second one.
No. Yeah. So this is the point. So this impurity is sitting at the origin and it breaks the translation. It breaks translation then. So the momentum is not conserved. Yeah. In particular, in the language of action, this just looks like adding to the action term. That looks like this. dt psi dagger t 0 at the origin sigma vector psi t. Okay. So
sorry, is it just the origin or it's some tenses of the defect? The first line I don't see where origin is.
well, it's just the fact that I'm integrating over all momentum and there's no. I mean, this is if I Fourier transform this thing, I would get well without the time I would get this right.
There's no phase there, k-dependent phase. That means the origin.
Ah, okay.
Yeah. There's no. Yeah, that's right. There's no.
That's right.
In this term, there is the epsilon k, which represents the energy, and in this term there is.
So this is just one defect at the origin?
Yes. In space-time, this is a line, but in space, it's just an impurity that sits at the origin.
Oh, okay.
Yeah. So this is a line defect from the point of view of space.
Okay.
It's time dependent, right? Time dependent fluctuations.
Yes. Yeah, you could consider S to be time dependent, but right now I'm considering just the impurity sits there. Yeah, at all times. So.
And just for context, the first integral in the Hamiltonian, is that an interaction between the electrons and the phonons?
No, this is just free for.
That's just the free.
Yeah. So I'm neglecting.
You're
phonon.
neglecting that.
Yeah.
You're neglecting that term.
Yeah, I'm neglecting phonon
Yes,
contributions.
good, yeah,
So
right, I agree.
I'm assuming
You're
that.
just explaining why it goes up at very, very low temperature.
Yeah, I'm just explaining this part of
Good,
it.
got it,
I'm not explaining
got
this
it,
part.
got it, got it.
Yeah. Okay. Any other questions? Okay. So we can take this model and start doing calculation. So how would we compute resistivity? Resistivity usually in field theory is computed by computing the 2-point function of the current at finite temperature, and so for that purpose you need to start by computing the 2-point function of just the fermion, say psi dagger of tau 1 r1 and psi tau 2 of r2. Right. You just compute this 2-point function, and let me just explain what are the diagrams that you would draw to calculate this 2-point function. Say this is a line defect; it sits at r equals 0, and this is the time direction. This is how the time goes.
Sorry. Why is it the line? Because there it sits at the origin.
Well, it's a line defect in space-time. It sits at all times.
Oh, okay,
So
okay.
now I will. Well,
In space, it's just
in space,
it's
just a
just
point.
kind of one
Yeah.
iron atom.
It sits at all times. Yeah. It's just a iron atom at the origin state. Yeah. I mean, You can consider more general cases when you have more impurities, but I'm considering just one. Okay, so then you would compute this two-point function of fermion, and so now what Condor did was he just did perturbation theory in this variable lambda, like assume lambda is small and do perturbation theory, right? So you can start doing perturbation theory. There will be a term which would be just lambda to the 0 term, which would just be the leading pre-theory two-point function. Then there would be a correction to it, which would be order lambda, like because this line has a psi dagger and a psi, so this vertex essentially has 2 points, and you can compute this two-point function. And there would be another term which would look like this. This is the order lambda term and order lambda square. I'm not going to compute these things, but let me just tell you what the answer is. So if you compute this two-point function of fermion, and then you compute the two-point function of the current and extract what the resistivity is, you find this formula as function of lambda. You find the lambda mu lambda square. Okay, so let me just write down the formula, and then I will explain what it contains.
Is it really like delta function potential or something? This thing?
Yeah, it
It's
is.
just a delta function
It's
potential.
delta function.
Standard problem in quantum mechanics.
Right,
Delta
yeah.
function. Okay.
Yes, yes. Well, yeah. So then you compute the resistivity as a function of temperature. This T is the temperature, and this D is the bandwidth. So as I said before, I'm considering low temperatures. So yeah, I'm going to consider only fluctuations which are very close to the Fermi surface. So I'm looking at this momentum K is just Kf Fermi momentum plus K prime, and this K prime is bounded by D. That's the D that appears here. Now you notice that this function essentially, if I increase the temperature, this will increase. Like as T goes to C, sorry. As I decrease the temperature, the resistivity increases. This formula explains this curve, but it doesn't quite explain this curve, because it tells you that if T goes to 0, this resistivity will go up. That's also not what happens. At exactly 0 temperature, resistivity does go to 0. So, and the reason why we get this, this result is correct up to a temperature which is. So first of all, let me remind you, we're doing perturbation theory in lambda, right? And this perturbation theory is only valid up to a temperature called the Condor temperature, which is just T e to the minus 1 over mu lambda, right? So this perturbation theory will break down at very low temperature, so this explains this resistivity at intermediate temperatures, but not at very low temperatures. And if you want to understand now, in the language of quantum field theory, this parameter lambda is actually a marginally relevant parameter, which means that as you go to lower energies, this parameter grows. And to really capture physics of low temperatures, one has to consider the normalization group flow of this coupling lambda. And it turns out that, this was done in 1964. This was before Wilson invented the normalization group. And this actually led to a lot of developments, which in the end did contribute to development of RG language. And it turns out that this coupling lambda flows. So if you this is lambda equals 0, this is lambda less than 0, and this is lambda bigger than 0. And it turns out that lambda equals 0 is not a fixed point for this coupling. If you start from lambda less than 0, it will reduce. But if you start from lambda bigger than 0, it will grow. And there is a fixed point somewhere here. And one should really, if one wants to understand to go to temperatures below this Condor temperature, one should do perturbation theory around this fixed point, not lambda equals 0. Okay. Any questions about?
Yes. Can you give an intuitive argument why lambda behaves this way?
Well, first of all, you can First of all, you can do calculations of along this line, and you can see that if I just compute the 2-point function on the line, it's like logarithmic. It's not power law. So that tells you that this lambda equals 0 fixed point is not a conformal fixed point. I'm not sure how to think about it in more intuitive way.
It's like it aligns spin of adjacent electrons with itself, and that's why the effective coupling increases. So I have the effective enhancement of the spin coupling. Like the spin, actually, what you see is not this spin exactly. It's a spin with electrons that surrounds it, and it goes that if you have a magnetic phase, it will increase the power of this.
Yeah,
that's why you expect to see this behavior.
Yes, that's a very good way to explain it. Yeah. Okay, so this is all I wanted to say about the Kondo effect. Next thing I want to talk about was the twist effect in Ising model. If there are no further questions, I will take this.
One, okay, ridiculous question. What do the properties of real metals at low temperature have to do with conformal field theories? Maybe you're going to tell us.
Well, I'm not going to tell you about metals. I'm not about Ising model, but in this case, you can really see that if you study this conformal fixed point, you can reproduce this curve.
Oh, it's because that fixed point there is a second order phase transition or whatever. So the theory,
this fixed point,
yeah, I see.
Mm-hmm.
Okay, good. That explains. Yeah, that's good.
Okay, let's move on to the next example. Next thing I'm going to talk about Ising model. So let me again remind people what is Ising model. So Ising model is a system of spins on a lattice. I'm going to draw.
Sorry, can I ask you about this Kondo? How can you do anything whatsoever if you have just one defect? Don't you have to sum over defects, whatever?
The dilute.
What's that?
You're studying the case where the defects are reasonably diluted.
So you can just ignore the effects of other ones.
So somehow just a single defect does describe the physics of dilute defects.
Right.
Very interesting.
So somewhere we assume short noise or something, right? Random distribution.
But the overall resistivity scales like the number density of defects in your metal? Like the minimum of that?
Yes, that's right. Yeah.
So what the CFT predicts for you is really like the scaling behavior. How does rho approach the final value at 0 temperature? The particular time dependence.
But who was conformal here? I am totally. Maybe.
Oh, just the claim is that this defect in the deep IR, so at 0 temperature, has some emergent conformal symmetry.
Of the resulting spin polarization or whatever?
Like various
in fuzzer direction, like you have this effective spin coupling that comes from the spin original and electrons surrounding them.
Right.
And if you go further and further, at some point you will see that there is some kind of defective one.
So exactly at the critical point, your theory is in fact conformally invariant.
That's right. Yes.
and that leads
All
to
these miracles. Okay.
and that leads to this particular scaling behavior, like in rho of temperature.
Okay. Let me.
And the prediction was matched physics, right?
No, this I know. For some reason, all these 2D things do work.
That's right.
Which is crazy.
So this is again a case where quantum field theory has things to tell about solid state physics.
Right. I think.
Okay.
Which is very good when the Simons Foundation is in New York.
Okay. So let's talk about 2D Ising model. What is 2D Ising model? It's just a system of a bunch of spins on a lattice. The partition function of the system looks like this. We have a sum over So you have these sites where the variables sigma live, and partition function, these variables can take values plus or minus 1. Sigma is either plus or minus 1. And the partition function is obtained by just summing over all the spins, sigma j jk, which is plus minus 1, exponential of minus beta times the Hamiltonian. And this partition function is a function of variable k, and this Hamiltonian is also a function of this variable k and sigma. And I will explain. Now we write down what the Hamiltonian of the system is. It's just the interaction between. It just includes the interaction between nearest neighbors. So the Hamiltonian is given by minus sum over j and k. Well, j runs in this direction, say, and k runs in this direction. And we have variables sigma jk, and then there's interaction k. K is the interaction strength between intersite interactions, and then there's sigma j plus 1 k plus sigma j k plus 1. So that's the interaction. It's a very simple interaction. I'm talking about ferromagnetic. Beta is the temperature. Beta is 1 over T. And this partition, yeah, and so this if you lower the temperature, this Hamiltonian will want to minimize itself. And how, since this sign is negative and k is taken to be positive, the way it would minimize itself is by spins all aligning together. Right now, let me consider a variation of this. Let me change the couplings. So k is a set of couplings. Let me change it to set of couplings k tilde. What is k tilde? K tilde is just I will change some of these spins to minus them. Let me correct chalk, and let me do the following. I will flip a bunch of these spins. So a bunch of these links. I will consider this path. And what I'm doing here is I'm k tilde the set k tilde is defined such that these couplings k go to minus k along this path. Let me call this path down. Right, and then let me define. So this line, this path ends at 2 points. Right, there's this point. Let me call this R1. Let me call this R2. And I'm going to define an object.
So do you flip the links which are crossed by this path? Or what?
Yes, I will flip all the links that flip all the links that are crossed by this path.
All right.
Yeah. So now if this line was now this is finite line, but if this line was infinite, and then if I flew to, so first of all, if I flip this link, then these two spins now don't want to align; they want to anti-align, right? If I was at 0 temperature and this line was really infinite, then all the spins on one side would be opposite of all the spins on the other side. This defines a domain wall in this theory. In this 2D example, domain wall is really just a line, but in 3D case, it would be a wall.
And just to be sure, I said you're like, we should imagine you just interchange the vertices. That's what
No,
means
he
about
changes
flip
the
link.
coupling
I wanna know if
constant
he
on the
means-
link.
What do you
He
mean
doesn't
about
interchange
flipping the
the
link? I
vortices.
want to be sure. But should I think of it as a defect, like you move the vertices? Or
No.
No, I'm not moving the vertices. I'm just flipping the interaction strength so that these two spins now want to anti-align, not align. So
or
this
just
Hamiltonian.
make it the opposite. Okay.
This Hamiltonian depends on this coupling constant k, and I'm saying that I just flip some of these.
Just locally. Okay.
Yes, yeah. And then this operation defines for me a partition. Now there's a partition function, right? Partition function depends on the coupling k. So now I have a partition function called z of k tilde.
Sorry, why does it make sense? Why should we be interested in this strange arrangement?
Well, I will. Yeah, I mean, first of all, you could. Are you saying how would I do it? Like really? First.
So it is realizable experimentally, you're saying? Or what?
Yeah. So you can realize it in Monte Carlo. Yes.
No, I mean, I mean, there are stars which are blue, but there are no stars which are yellow, green, or something. So why is it an interesting system? Is it realized in condensed matter, or?
So one application is that this will define this. So this defines an operator living on this site, which is called the disorder operator, and this is useful in solving the 2D Ising model. Say.
Your lattice could have disorders. Some kind of like.
So real disorders in real systems
yes.
sometimes will be arranged in lines.
Yes, like.
I mean, first of all, the fact that this is a line doesn't matter. I will show that it doesn't. This partition, this does not matter where the line is. I can change.
Perhaps I'm not formulating myself clearly. I'm asking, does it correspond to anything in reality? Ising model supposedly describes second-order phase transitions and various circumstances. What does this describe?
I mean, you could, as Fedor said, you could have a disorder in the magnetic system, and that would be described by this.
Like point defects?
It's like a vertex.
Yeah.
Not point defects. It should be line defects.
But
No,
this is
it's pointing in space. This is like a Euclidean.
this
Well,
is a
this
2D.
is Euclidean.
I mean, here this is the. I mean, if you think about quantum field theory, it's Euclidean.
Are we doing statistical mechanics of two-dimensional Ising?
That's
and that
correct.
description in terms of this quantum field theory is just a two-dimensional Euclidean quantum field theory. So it's one-dimensional. So when Himanshu think about one-dimensional, it's one-dimensional in the space-time.
So can I think 2D Ising or not?
Yes, this is 2D Ising.
In 2D Ising,
Yeah.
these lines of flipped links,
Yes.
flipped sign of interaction, what do they correspond to in real life? Can I create this system in a laboratory?
Didn't he tell us it was a 1D system in real
He said,
space,
but then he
and it became
retracted.
2D?
Well,
This is the two-dimensional.
I'm just talking about 2D Ising model.
Yeah.
What you see is what I'm talking about.
So it is 2D Ising.
It's 2D Ising model.
How in
Out of the
2D
way.
Ising I achieve the flipped interaction sign?
I mean, you could have a disorder in the. You could have a impurity here, which would make sure that as you go. So what happens here is that around this point.
So Ising with impurities sometimes reduces
That's
to
right.
what you are considering.
Exactly. Yeah.
Wonderful. That's
Okay,
satisfactory.
Okay, good. Yeah. So now what I'm talking about is that this flipped spins. This defines a partition function z of k theta, and I can define an object called mu of r1, mu of r2, which is the ratio of the ratio of this new partition function divided by the original partition function. Now, what is r1 and r2? R1 and r2 are these points, and I claim that this defines a correlation function of a disorder operator, which I refer as mu, and it's defined as the ratio of these two partition functions. Now, what I want to show is that this line is path independent. What I mean is that as long as this as long as this path gamma connects these 2 points r1 and r2, that's all that matters. You could draw a different path and you would still get the same partition function. Now, to show that, it's very simple to show that. We call that in the partition function, you are summing over spins, right? So these spins are really W variables. Partition function does not depend on what the spins are. It just depends on the links. So what I will do is I will take a bunch of spins, which I will label by circles, and I will flip them. I will start with the partition function, right? And I flip these spins. If I flip the spin, what effectively does is rather than this coupling being minus k, this coupling becomes minus k, and this coupling becomes minus k, right? So what I did here is this becomes a usual link, and this became the modified link. Now this link is minus k and this link is k. This is simply because this k connects sigma jk to sigma j plus 1k. And if I flip one spin, it will flip the sign of coupling for all the links that are connected to this spin. So it will flip the sign of this coupling and this coupling. essentially that's what I do. So if I flip these 3 spins, the claim is that now the path, now these spins are flipped.
Actually, people from this side can't really see what you're drawing.
Oh, okay. So
Yes, you can alternate.
Like that.
You just have to go transparent,
yes. So
like a real physicist. Go transparent.
Open science.
what I just said is that what I originally had was that I had this path gamma, and if I actually I can lift it. Okay. What I just said is that I had this path gamma, right, along which I had flipped the sign of coupling. What I'm claiming is that since these spin variables are just dummy variables in the path integer, if I flip these 4 spins, effectively what that would do is that would define a new partition function z of k tilde prime, which is the partition function when those links are the same as the original partition function, but these links are flipped. So what I did was I have still the same 2 points, but now I'm defining the partition. I'm defining a partition function where the links along this path are flipped. Okay. So what this shows for me, first, it shows 2 things. One thing is that if I flip the links along a closed path, that just means nothing. That just means I'm doing nothing. If there are no endpoints of this path, that means I haven't done anything. I just written down the partition function again. And second thing that it shows is that this domain wall really just depends on the endpoint, and the endpoints define. This also means that the endpoints are meaningful. In 2D Ising model, these endpoints are local, like these are point-like, right?
I retain my confusion, and I think actually Andre maybe shares it. You're talking about flipping links, but really the fundamental observables are the spins, right?
Right. Okay.
So what is it you do to the spins to do what you're calling flipping the links?
I'm flipping the interaction between the spins.
You're changing the sign
I'm changing the sign of the interaction.
of just that one pair.
Yes, of a bunch of pairs. Yes.
Yes, but it's
Well, for instance, I could.
okay.
And he claims it is doable by introducing impurities into corresponding sites.
Yeah, that's what one like. Okay. Continue.
Okay.
Well, and I think one of the implicit things is that for you, the sign of the sigmas is just a label, an arbitrary label that's been chosen. So you can reverse the label.
That's right. Yeah.
And it doesn't change the physical system. So it's like a coordinate freedom in a certain way.
Yes, that's right. I mean, yeah, that's correct. So the point is that in 2D Ising model, this is really just a point, but I could do the same thing in 3D Ising model, right? Now imagine there is,
Well, one of the things that confuses me is supposing you substituted some impurity whose intrinsic coupling was the opposite. It would affect all of its neighbors. It wouldn't affect just that one neighbor. I don't see how you can flip just one link.
So,
I mean, I'm trying to think of.
I mean, maybe you can build the
physically.
system with, on the links that you want to flip, you can put some additional impurity on the link itself. And that could probably flip the
Oh, is that how he does it?
The links are
At least it's doable in principle,
Yeah,
right?
yeah.
All these lattices are crazy. You can put a new thing on a link.
and to tell you something, you could also do it by introducing a magnetic field, say, right? I mean, let's say if I wanted to do it semi-infinitely, right? If I wanted to introduce a line defect, which was which was throughout the lattice. So what I would do is I turn on when I'm lowering the temperature. Say I turn on a magnetic field above, but not below, right? And then when I lower the temperature, all the spins above will be pointing in this direction. But then, okay, so I could turn on opposite magnetic fields in opposite directions, and then I lower the temperature. That would prepare a state for you which has a domain wall. Right?
I think the confusion is that you're kind of talking about two different things, flipping the links and flipping the spins. and flipping the coupling. And what you're saying now, that kind of flipping the spins on one side of the domain wall, that's equivalent to flipping the coupling here. And I think that's kind of wasn't said explicitly in what you, and that's why people are a bit confused.
Not me.
It's essential that it be 2D for that to work, I guess, that's part of it.
No, you
No,
could.
no, you can do it along any plane in
You
5
could,
dimensions.
Well, that's right, but you couldn't just flip one line in 3D, just one, anyway, but
No,
you're
you
doing 2D, so
You
I
could
won't
flip the
worry
whole
about
plane,
3D.
yes. So yeah, that's what I'm going to talk about next. So if you can do this, you can play the same game in 3D. Now imagine, there's a whole lattice coming out of the blackboard. And in that case, you could have a plane where you would, flip the links on. And that would define for you, now, as I said before, that would define a domain wall, which would again be topological by the same arguments that I presented. Like this argument will go through in any dimension. So this domain wall would still be topological.
Sorry, if we, for example, describe the resistivity curves for X and Y, because we have a line over there, are going to be different, or like a quantum Hall effect we can see in this type of systems. Because I mean, I don't know too much, but if I see a line on this direction, it's going to destroy all the symmetry in translation like this or translation like this. Like, does that have an effect on the observables when I put the defects?
Yeah, it will have effect on observables. Yeah, I will talk about that. Yeah, It will have effect on critical exponents and so on. Yeah.
But just I want to restate one more time, just because I think it's so cool. You just taught me something that I didn't understand at all in the Ising model, which is that you could reverse a set of signs in this lattice, but if I can draw a path, a closed path that cuts through those reversed edges,
that does nothing.
then you could just relabel what you call positive and negative, and we're back to the original Ising model.
That's right.
That's gorgeous. I had not understood that at all. That is really a beautiful thing.
Yeah, so that basically tells you that, that is
the
a consequence.
defects have to be topologically non-trivial to be interesting.
That's right. So this domain wall is a it's topological domain wall. It doesn't change energy, so you can shrink it to a point, and then you're done with it.
Good.
Yeah.
Gorgeous.
Okay. Any other comments? Okay.
Beautiful.
Okay. Now we do it in 3 dimensions. Okay. So in 3 dimensions, you have this domain wall would be a surface, and this would end on a line, right? Because just because a 2-dimensional surface ends on a line. So in that case, this mu, it's wrong to write down mu of R1. This mu really supported along a line, right? And now you can ask, now once you have a line, you can ask if this defines for you a conformal defect. Now what do I mean by a conformal defect? For this purpose, I just mean that, so the end of this domain wall is a line, and I can consider excitations localized on the line, right? I could consider operators localized on the line. Let's say this direction is y, and for this line to be topological, or for this line to be conformal, what this would mean is that if I write down, if I compute a 2-point function of this operator, it should be power law. It should go like some coefficient divided by y12 to some power delta, right? And if this was not conformal, it would be exponentially decaying or something else. Okay. So now this defect was studied in Monte Carlo simulations. You do exactly the way I described. You can you start with the 3D Ising model and you do this Monte Carlo, except that you flip the sign of links for a particular surface, and then you can study and then you can study what happens to these what happens to the correlation functions of the spins, which are really close to the line, and it was found that this defect is really conformal. Okay, so let me discuss how this line defect should be described in the continuum model. Okay, so let me start with a free scalar, just for simplicity for now. I will start with this simple action, which is just the action of a free scalar field theory. Right. This satisfies equation of motion, right? Box y equals 0.
Sorry, what does it mean conformal? It means you tune the temperature and at some temperature it becomes pure power law? Or...
That's right. So in the bulk, that is true. And so if you are far away from the line, once you tune the temperature to the critical point, then the correlation functions become power law. But that does not necessarily imply that on the line it should still be power law.
Right, but this is what I'm asking. Should you tune, is there a special phase transition temperature for the defects on the line?
For this particular line, no.
They will always be power laws?
Yes.
No matter what's the temperature?
As the same as the bulk conformal, bulk temperature.
Or the same as bulk. So when bulk is critical,
yes,
the defects on the line are also critical.
That's right.
Okay.
This is very special.
So this is not true about the condo line defect that I described before, for instance, because there was a coupling lambda, right? And as I said, if you just compute the correlation function on the line for that condo line defect, it will be logarithmic. It will not be power law unless you tune lambda to the conformal, to the fixed point. But in this stretch, this is what is called as, this line defect is what is called as stretch defect or monotonic defect in the Ising model. And for this defect, it's special that there is no parameter on the line. If the bulk is conformal, the defect is conformal. Okay, so we want to describe this, how to understand how to describe this defect in the continuum model. And in the continuum limit, this 3D Ising model may be described by a scalar field theory. So that's for that purpose, let me start with just the free scalar and let me talk about how to describe this line defect on the free scalar, right? There are three directions, right? I will write them as R, phi, and y. And the line defect sits along the y, at r equals 0, along y direction. Yes. Okay. And the way this fact about the lattice that implements itself in the shows up in the continuum model is by this requirement. We require that as we go around r equals 0 point, y, which is the same as minus phi r, let me call it. Let me not bend differently so to avoid confusion. Okay, so the way we impose this requirement, this monodromy requirement, is by saying that as we go around this line, the scalar field phi picks up a minus sign. Okay, and then what we can really do is, so we can now try to study what this does. The simplest thing we can do is we can just expand the bulk scalar in powers. So in powers of the distance to the line, right? This is just like a Taylor series expansion.
Sorry, what is this complexification? Why is it phi plus I pi?
Wait, sorry, it's 2. I just meant,
okay.
Yeah, I just meant that, when the scalar.
Because in your world, everything is possible.
No, not everything.
I have to ask. Okay, so it's 2 pi. Okay,
it's 2 pi. Yeah, you go around the line.
It's not as crazy as usual. Okay,
it's never crazy.
And that, you impose that, or
yeah, I impose.
You impose this. Okay, good.
Yeah, this is how I define my line defect.
Yeah, fine.
Yeah, I'm just saying that.
I see. This is
the
continuum limit, and this is like some kind of continuum limit of that.
Yeah, in continuum limit, this is how I define my line.
Got it. Yeah.
Okay. So now I can just expand this operator phi. So what I can do is, as I said before, there are operators living on the line, and I can expand my bulk field in powers of the distance from the bulk, and right now I'm just doing something that looks like a Taylor series expansion. these are the operators that live on the line, and this is the bulk operator. And since I'm expanding it, I should compensate because this bulk operator and the defect operator may have different dimensions. So I'll compensate that by adding this. Okay. Okay. So now the fact that this scalar has to pick up a minus sign implies that this number s that I'm summing over has to be half integer. It has to be half integer. That's all. If s is integer, then I have no defect. If s is half integer, then if s is integer, I'm just doing a regular Taylor series expansion. But if s is half integer, then this imposes this this condition, right? And then it turns out that well, in the free scalar, this scalar phi has dimensions which are just 1/2, right? And you can impose this equation of motion to determine what is the scaling dimension of the operators living on the line, the psi. And it turns out that the leading operator that, well, so in this expansion, there is the operator that, as r goes to 0, this term is dominated by the leading, the term with the lowest value of delta psi. And the lowest value of delta psi is 1. Or in particular, it is half plus s, and the lowest spin is half. This is just 1. So this s is also called the spin of the operators living on the line, right? Then you can go back to the lattice model, and you can ask, you can compute these 2-point functions, and you can ask what are the values of these dimensions that the lattice predicts, like that you get from the Monte Carlo, right? And it turns out that this bulk scalar phi doesn't have dimensions half, right? It has dimensions 0.51819. With accuracy of plus minus 7, and this operator living on the line has dimensions 0.9187 plus minus 6. Now I want to emphasize here that this number is not just this number plus a half, right? They are very different, which means that which essentially means that the operators living on the line have different anomalous dimensions. So what is anomalous? So this is the bare. This is what is called the bare dimension. This you can just get by dimension analysis, and the bare dimension tells you that the operator phi should have a dimension half, and the operator psi should have dimension 1. And then these operators get anomalous dimensions from interactions, and when you do this Monte Carlo on the lattice, you see that these are the values of real dimensions. And what these formulas indicate is that this defect is really a non-trivial defect. Then this does change the critical exponents of operators living on the line. Okay, so now how do we calculate these numbers, right? I want to give you a flavor of how one would go about calculating this number analytically.
Also, I mean, maybe I'm wrong, but can we also see that it changes the commutation relations of phi? Because then it's like a Fermi, that phi goes around and you pick up minus sign.
Yes.
But if it would be a normal scalar, you go around to phi and you don't pick anything.
Yes.
But if you're not at 0 and you do the same calculation at a different r, you pick a minus sign or you pick a plus sign?
You have to go around the line.
So it has to be centered at r equals 0.
Right. So I mean, this is
So it commutes everywhere, but anti-commutes in only one line. I mean, the commutation relations of phi with itself, what would it be? Because that's a scalar, but like a weird scalar.
But only at r equals 0, this phase picks up a phase, not from r.
So it's like a fermion locally.
But it's not I wouldn't call it a fermion. It still is a scalar.
But how would you write the commutation relations of a scalar that anti-commutes?
Well, it doesn't quite anti-commute though, because
the phi's are scalar, they commute with one another.
Yeah.
I think the one that potentially could be fermions are the size.
Yeah.
And the non-trivial commutation relation that you want to study is when you exchange the order of psi on the line. And I don't remember if it's indeed there's a minus.
there's
sign.
two scalars.
Right.
The size are also scalars.
They're also scalar.
Yeah.
Yeah.
Okay. Okay. So let me just quickly show you what. Okay. So now, how would if one wants to compute this number and this number, how does one usually do it? So, so the point is that the Ising model is not described by a free scalar in 3 dimensions. It's described by interacting scalar, and for that you have to consider really interacting action, which is described by a scalar that is interacting with a. There's a 5 to the 4 interaction that one has to add in order to describe. Now this.
The first is a square, right?
Yes, this is square. Yeah, there's a 5 to the 4 and the scalar interact itself, and to describe the Ising fixed point, one has to. This lambda is not small. This lambda is large. So now, how does one go about doing the calculations? So one way is to do there are various methods to, well, one way is Monte Carlo. You could say just we are done. We did the Monte Carlo. We are done. Another, but we could also like do other things. We could do perturbation theory. Now perturbation theory in lambda, but perturbation theory like in 3D Ising model, lambda is not small. So the one way to do perturbation theory is to go in d equals 4 minus epsilon dimensions. And if one does that, then this coupling lambda is of order epsilon. And so one can do this, and then one can compute what the 2-point function of the. Okay, so how would one compute the scaling dimension of the operator localized on the line? So again, this is a line again, and then one wants to compute this 2-point function, right? So the leading correction from this coupling would come from a diagram that looks like this. This is lambda 5 to the 4, right? And this is a 4-point interaction, and one would compute this diagram, and then one would calculate how this behaves, right? And in fact, this calculation was done, and one can compute, so you could ask, like, I'm interested in 3D Ising model, right? Why am I doing 4 minus epsilon? It turns out that one can calculate, in this scheme, and then one can, at the end of the calculation, set epsilon equals 1. Now this could sound like a very bad thing to do, but it turns out, at least for this quantity, if one computes this in epsilon expansion and sets epsilon equals 1, one finds 0.917, which I would say is pretty good, right? You had tree theory, which was dimension 1, and then you had Monte Carlo, which is 0.9187, and you get 0.917. This is one scheme to do perturbation theory. There's another scheme one can do, which is the so-called large n expansion. So what for large n expansion, what one does is rather than one scalar field, one considers n of them. Right. And then one can exactly solve this model at large n.
Isn't it exactly the same as they do for 3D Ising model?
Yeah, but I'm saying, that's true, but right now I'm considering the 3D Ising model.
I understand, but both epsilon and n expansions also work okay for 3D Ising, correct?
That's right, yeah. For this quantity also they work okay. So I'm saying that now, what can be done about this one. So this is the bulk along, regular.
This is the standard.
This is the standard result, and this is the result for the operator localized on the line. Okay, so one can also do, exactly. So one can also do this large n expansion, and then in the end send n equals 1, which is also sounds like a very bad thing to do, but one does it and one finds the result, which is 0.786, which is pretty bad because it's very far away from this, but the hope is that if one does it for O2 model or O3 model, one will find a better result. Yes.
This number you quoted for the epsilon expansion, is this like first order or is
This
this
first
like
order
some
epsilon.
fancy?
This is just this diagram.
Ah, okay.
And that's why, okay, so yeah, that's why I'm saying it's pretty good, because you just, this is just order epsilon, like it has order epsilon square or correction. And this is also just the leading order in 1/n expansion. And this gives you this number, 0.786. And yeah, and then another way to calculate these numbers is by doing.
So is that systematically improvable? So as you go to a higher order in lambda, etc., or higher order in epsilon?
Yes.
Even though epsilon is 1, do you expect to find better and better agreement?
Yeah, it turns out that the perturbation theory really is not in lambda, but lambda over 4 pi squared. So this is a small quantity. And that's because that's just when you do the calculations, it turns out that higher loop diagrams are not just suppressed by powers of lambda.
And what is the effect of lambda? I mean, what is the value of that expansion parameter for 3D Ising? No, lambda over 4 pi squared.
I don't remember, but I think it's something. Yeah, I don't remember.
But less than 1.
Less than 1, yes. Yeah, it's not 1, yeah. Yes. So yeah, you can do large n, and then you find this result. And there are other ways to compute this quantity, which is the last way I can talk about is this so-called bootstrap, which is one just considers operators localized on this line and tries to do conformal bootstrap on the line, and that gives you a result which is 0.918, which is also a very good result. I mean, so Monte Carlo and conformal bootstrap essentially. Okay. So yeah, that's all I wanted to say about this.
Thanks, Himanshu, for a nice talk. We have some time for questions.
What exactly did you do? Some of it must have been done by other people.
This is okay. The only thing that was in my paper was this last result, the large n calculation.
So you did large n.
I did large n,
Which is not.
Which is not good for n equals 1, but I hope somebody will do Monte Carlo for n equals 2 or n equals 3.
Can you improve the n equals 1 by adding more terms?
Yeah, you can do a 1/n expansion. So yes, you can compute this in a 1/n expansion, right? You have some.
Yeah. But I'm saying, does a similar thing happen where the actual expansion parameter is smaller than 1, or is it like, would you expect this to improve?
This fact is just observational. You just write down the diagrams and you see.
No. I'm saying if observationally, does a similar thing happen for the?
I don't think anybody, at least for this, in the presence of the defect, nobody has tried to write down what the 1/n correction.
What about 3D Ising, normal 3D Ising for that thing?
Yeah.
Did they do 1/n expansion?
Well, it's just n equals 1. 3D Ising.
But few terms, I mean, have they done higher order? No.
In 1/n, no. Like the only thing that was done was
because for epsilon, I'm sure they have done at least 2, maybe 3.
Well, in the presence of the defect, no.
No. I mean for the usual.
For the usual Ising, yes. But people have done 1/n squared and 1/n cubed.
Oh, they do have 1/n.
Yeah.
Does
For the usual
the
Ising,
accuracy improve?
it does improve. Yeah.
It does improve.
For usual Ising, yes. People have done.
Because ultimately, I assume it is an asymptotic, right? Ultimately, you will run out of, but not at 2.
No, yeah. But at 1/n squared, people have done up to 1/n cubed, I think, for the usual Ising. But in the presence of the defect, people haven't done. I mean, it's harder because you break translational symmetry, right? Because you have a line.
Are there real life experiments? Why are you so eager to compute this number?
I don't think there are any experiments which have seen this. No.
You just like the math of it.
Yeah.
Conda effect,
Conda effect.
No, I'm talking about this defect things. This thing.
This Ising defect, I don't think there are experiments yet.
So you do it for the pleasure of beautiful math.
And hope that there will be experiments.
Monte Carlo.
But also real experiments.
For real experiment.
You could see it. I think you could see it in real experiments, but people
I mean,
haven't
you
seen
can
it.
imagine some kind of impurity in the like a uniaxial magnet, some impurity that some impurity like a vertex, so you go around it, the spin flips by the sun. Whether that can be engineered, in some real life lattice system that.
Can I ask real quick again? The minus sign, like I didn't understand going from the lattice model with the defects. Like, why should you look for phi going to minus phi?
Yes, so good. I mean, when I flip, so in this 2D example, when I flip this link, what happens? So one thing you can imagine is that if you go to 0 temperature, these both spins will have opposite signs, right? If you just because this link is and all the other spins will have the same sign. So as that suggests that as you go around the disorder operator, it will pick up a minus sign, and the continuum version of that is this.
Because and maybe I'm misspeaking, but in my mind that relates to that there's this labeling, because you can label what counts as positive or negative. You can't actually localize. All you know is that there's a defect in this cell, but you don't know where it is. And it arises at, you cannot come around here and end up at the same sign.
That's right. Yeah, you have as you go around
at 0 temperature.
Right. You would naively think that you have marked your links,
but
in reality you haven't. You can move them just by relabeling signals.
That's right.
Yeah, I agree.
That's very nice.
Fine.
Because it relates the active symmetry of the lattice that is translationally independent to the passive symmetry of how you actually just describe the system. So it's very nice model for symmetries in physics.
Yeah, this can be made like more precise. This there's a Z2 gauge symmetry in this sizing model.
It's a gauge symmetry, right?
Yeah.
How can I constrain my defect? So like you said that phi goes to minus phi. If I take a complex scalar, I can say like a.
You can pick up a phase rather than.
That will have some classification of all possible defects in my theory.
I think it's very hard. I don't think it has been done,
but you can put some kind of bounds on how this
So I meant like in general. Can I say that like this theory has finite number of defects? Or is
no, that's not. You can ask about universality classes.
Yeah, like
you also work on this stuff.
Yeah.
But
not this particular model.
In this Ising state where it's this very simplistic model, you probably can say what all the possible defects are, right?
Yes. In 2D case, actually,
it's completely
in 2D minimal model.
That's it.
So
more or less. I mean,
into the two-dimensional Ising is completely caught.
And they live around this endpoint.
That's right. Up to an operator. If you don't have the extra dimension, it's just a point-blank operator.
Yeah, kind of a similar question. So when you go to the ON model, you get new defects?
Yes, so this is what was studied in this paper that I mentioned. So if you have ON model, so basically this is called monodromy defect, and it's classified by the symmetry of your action. So in ON you have ON symmetry, right? You can imagine that pi I as you go around, pi plus 2 pi y is not it's some matrix G I J phi j, right? R pi y, and the special example of this is when this is -1 for all I, but for all ij, but in general you could just imagine a matrix where G I J is the element of ON. This is the monodromy defect.
Yeah, so my question is that, can I understand, like, will that somehow mess up my perturbation expansion?
No.
Do they interact at all? Do I have to, can I just focus on, like, as I take this n to 1 limit, is it only like one line that becomes my one I'm interested in, and that n to 1 limit, or do they somehow mix?
Well, okay, if you want to consider more general, you have to consider, if you consider a complex scalar, then this is similar to like if you just consider a complex scalar, then this picks up a phase as you go around. So if you want to, so good. So, but then there's also a limit of that when this phase is just phi, right? In that case, both these scalars pick up just a minus sign. So there's a limit of this. Well, there's a limit of this matrix when all the scalars just pick up a minus sign.
I think what Jack may be asking is that there are just so many more defects in the one case.
Yeah.
And the question is, do they all have the same limiting behavior as n equal to 1?
Well, you can, yeah, so.
That's your question, right?
Yeah, and can I understand, like, I was curious because it doesn't seem like you're adding a lot more defects when you go to the epsilon expansion. Is this, can I understand, like, why that's better, or, like, converges more closely to the Monte Carlo answer? Because, for instance, I'm not adding a bunch of extra lines.
Yeah, I'm not sure. You're saying that, is that why this n goes through one limit does not
like,
work
for
as
instance,
well?
do you add defects when you go to the epsilon expansion, or no?
No, I mean, if you just have a single scalar, then there's only one more, because this is because the symmetric group is just Z2, so you can just study Z2 line because here.
So I was just curious. That was more
Yeah, it's a good question. I'm not sure. I think, yeah.
So in view of time, let's maybe thank Himanshu again. Then leave more questions.
Do solid state people, so to speak, listen to you?